Hello class. In lesson 2.5, factoring the factor and remainder theorem, what you're going to learn here is how to use the remainder theorem to evaluate polynomial functions at x is equal to a constant. And you'll also learn to use the factor theorem to determine if a binomial is a factor and factor the degree 3 or 4 polynomial, and then completely find the other remaining factors of a polynomial. This begins by going over the remainder theorem. Now, what the remainder theorem states that if a polynomial function f of x is divided by x minus c, then the remainder is equal to the value of the function at this c that we're subtracting from the divisor. So what this essentially is telling us is that we can use a method that's called synthetic substitution in order to evaluate a function, a polynomial function, again, specifically a polynomial function, at a specific value for x. So for example, here, if I want to evaluate this using the remainder theorem, and I want to evaluate this function here at 1, -2, 1/2, and 2, I can do it the old-fashioned way by plugging in the number 1 in for the value of x. So let me do that with the calculator. So I can do 2 times 1, raise that to the third power, minus 7, replace the x. Oops, let's delete that. There we go. Minus 7, replace the x again with 1 again, and then add 3. And that gives us a value of -2. Well, I can get the exact same answer. Let me move this out of the way. I can get this exact same answer of -2 by using, again, synthetic division, or in this technique referred to as synthetic substitution. So I start by putting the 1, the value I'm going to substitute in, on the outside of my synthetic division setup. Since I have x to the third power, that's the highest exponent, that's the degree of this polynomial, I start with 2. But notice that I do not have an x to the second power. I skip from x to the second to x to the first. So I'm going to use a 0 to hold the place value for that power of 2, that quadratic term. Then I have my linear term of 7x, and then 3. And again, just to recap what the remainder theorem states, what the remainder theorem states is that I'm going to get the same answer. I'm going to get the answer of -2 at the remainder. So this last number right there is going to equal to -2. So using synthetic division, I'm going to bring down the 2 and multiply 2 with 1, add 2 with 0, multiply again with 1, add, multiply, and then add again, and I end up again with -2. So you see this remainder matches again exactly to the value I got by doing the normal substitution instead of this synthetic substitution. And that's what the remainder theorem is simply stating, that I can evaluate a function by using this technique. So let's use the same technique with the remaining problem. So right here, using synthetic substitution and evaluate the function at -2, I will put -2 there. And using again 2, 0, -7, and 3, I'll bring down the 2, multiply, add, multiply, add, multiply, and add, and my answer is going to be 1. So f of -2 is equal to 1. Now for 1/2, same thing. So I bring down the 2, multiply, add, multiply. This is going to be 6.5, -6.5, multiply, and add, let me move the 3 over a little bit, and add -3.25 with 3, that's -0.25, and that right there, the remainder, is your answer. So f of 1/2 is equal to -0.25. And for the last one, 2, 0, -7, and 3. we end up with 5. So f of positive 2 is equal to positive 5, and f of negative 2, let me write this a little bit nicer, this kind of looks ugly. So f of negative 2 equals to positive 1, and f of positive 2 is equal to positive 5. So here are your values to your functions. F of 1 is negative 2, and f of 1/2 is negative 0.25. So there you go. Awesome. Now, let's see. Pause the video and try this example for yourself. Okay, let's check your work on this example. Now, notice that on this example, we have the highest degree is x to the 6th power. Notice that we do not have an x to the 5th, an x to the 3rd, nor an x to the 1st power. So if we're going to use this technique of synthetic substitution, we need to have place values for those numbers there. So we start off with 2, but since there's no x to the 0th power, to the 5th power, I'm sorry, no x to the 5th power, we're going to put 0 for that place. We have an x to the 4th, which is 3. No x to the 3rd power, so we put a 0 for that one. We have an x to the 2nd power, which is negative 1. The coefficient to that is negative 1. There's no x to the power of 1, no linear term, so we're going to use 0 for that place value, and then the 3 at the very end. So start by bringing down the 2, multiplying, and adding, multiplying. Oh, I'm sorry, adding and then multiplying. That's going to give us 44, which is now 43. Multiply that with 2, that's 86. Add 0, that's still going to be 86. And then multiplying that by 2 is 172. Adding that with 3 gives us a total of 175. So there's your answer. G of 2 is equal to 175. So let's check your answer now for the second one for B. And I don't know why I make that so long. I don't need to make it as long. So 2, 2, 2, 5, 5, 5, 5, 4, 4, 4, 4 again, and 7. So G of 1 is equal to 7. Now, of course, with your 84, you can do this calculation just by replacing the value of x. But the idea here is to, again, not rely on the calculator and learn how to evaluate a polynomial function using this technique here. So for letter C, number 2, part C, we'll have 3, and then again the same coefficients. 21 times 3 is 63 plus 0 is 63. 63 plus times 3 is 188. Let me give some more space here so it looks like I have this lined up. -1, 0, and then 3 over here. So that's going to give us 187. 187 times 3 is 564. Plus 0 is the same, and then 564 times 3 is 1692, plus 3 is 1695. So G of 3 is equal to 1695. And for the last one, for -1, 2, 0, 3, 0, -1, 0, and 3. And again, just to recap, the reason I have zeros there is because I do not have So it's x to the 6th, x to the 5th, x to the 3rd. This is a 4, x squared, x, and then my constant. I do not have these powers here. So from 6, every term again, every power less than that has to be accounted for. And if one power isn't there, we use 0 as a placeholder. So that's why, again, I have those zeros there. And if you notice on this one, notice that all the ones I do have are even powers. I have x to the 6th, x to the 4th, x to the 2nd, and x to the 0 power, my constant. So this is technically an even function. And if you remember, the values of even functions, polynomial functions that are even, or any function that is an even function, it is symmetrical through the y-axis. So if g of 1 is equal to 7, g of negative 1 is going to equal to the exact same thing because of the symmetry. This is also going to equal to 7. Let's prove that again using the synthetic substitution. And the last one, again, look, is also 7. So you see, I got the same answer as letter B because this function is an even function. All of the exponents are raised to an even power. Even this one, this is technically x to the 0 power, and 0 is an even number. So with all of the exponents being even powered, that means that this is an even function. G of x is an even function. And because even functions have a symmetry across the y-axis, that means that for every xy, that's on the point, negative xy is also going to be a point on the graph. So the opposite x coordinate is going to have the same y coordinate as well. So since g1 is equal to 7, g of negative 1 also ended up equaling to 7, as you see right here when we did this synthetic substitution to prove that. Awesome. Very, very cool. So now that's the remainder theorem. Now, building up and moving on from this theorem is the remainder theorem. So applying the remainder theorem to the factor theorem, then we can identify if a polynomial is a factor to another one if the remainder is equal to 0. So in other words, if I use synthetic substitution and the last number, the remainder, is equal to 0, the value of the function is 0, then that means that x minus k is going to be a factor of the polynomial f of x. But again, this only works if our function is a polynomial. If it's not a polynomial, like if it's a rational function or an exponential function, any other type of function, then this theorem is not going to work. This only applies again to polynomials, just like the remainder theorem only applies to polynomials. So let's look at this example here and let's determine if these three appear, if these three over here are going to be factors to this function f of x, to this polynomial of f of x. Well, to do that, using synthetic substitution, we're going to see if our remainder is equal to 0. So since this example is x minus 2, that's my factor, x minus 2 is my factor, synthetic substitution would make that positive 2. And our coefficients are 2, 7, negative 4, negative 27, and negative 18. This one is not missing any powers. Notice that we start off with the power of 4, but then we have the power of 3, the power of 2, the power of 1, and our constant, which is technically x to the 0 power. Every power is accounted for, so we don't have to use the 0 to hold any of those places, any of those degrees. So now let's bring down the 2 and multiply. This is 11 times 2, 18 times 2, plus negative 27, that's 9. And 2 times 9 is positive 18, which is equal to 0. Since our remainder is equal to 0, that means by this synthetic substitution, x minus 2 is going to be a factor. So x minus 2 is a factor. X minus 2 divides this without any remainders. Now, by the division algorithm, I also now know the following, that x minus 2 times this right here, that's going to equal to 2x to the third power plus 11x squared plus 18x plus 9, this times x minus 2, my factor, multiplying these two things is going to equal to this. So instead of checking if x plus 3 is a factor to this entire thing, to this original thing, we can use now our answer, because I know that these two things multiply to give me this. So by the division algorithm, I can now verify if x plus 3 is a factor by seeing if it's a factor of this. If x plus 3 is a factor of my answer, of my quotient, then it's also going to be a factor of the original function itself. So instead of starting over and using the original function, I'm going to use simply my answer. So I'm going to put negative 3 on the outside, bringing down the 2 and multiplying. We have negative 6, adding it gives us 5, multiplying gives me negative 15, adding that with 18 is 3, and 3 times negative 3 is negative 9, which ends up becoming 0. So there we have it. So x plus 3 is also a factor. So what that means is that if I multiply x minus 2, my factor here of x minus 2, with my other factor of x plus 3, with this answer right here, that these three things multiplied together is going to give me that. So to prove now, to verify and check if the last binomial is a factor to f of x, I can again just simply use my answer. So instead of using the original one, I can then simply use my answer, because by the division algorithm, I know that these three multiply to give me that. So if I look at my quotients, the last answer I got, and check if x minus 1 gives me 0 as a remainder, then I will also know that x minus 1 is a factor. So let's check. So we're going to put positive 1 this time, because it's minus 1. And nope, we did not get 0. We ended up with 10. So since this is not equal to 0, that means that this last one is not a factor. So not a factor. So only the first two are factors. So multiplying these three will give us this. Now there's probably a possible way of factoring this, and there we can find the other factors, since we now have a quadratic, which is what the next example is going to be. So using the factor theorem, so let's look at example number 4. Using the factor theorem and the one given factor here, x plus 2, let's verify that x plus 2 is a factor, and using the answer, let's completely find the factorization of this polynomial. So let's find the other two factors, the remaining factors, given this one right here. So let's start by first verifying that x plus 2 is a factor by using synthetic substitution. So we're going to put negative 2 on the outside, positive 1, negative 10, and negative 8. And 0. So yes, all right. So as we can see, x plus 2 is in fact a factor, because we ended up with 0 at the very end. Our remainder is 0. Now, having given that we have x plus 2 as my factor, we now have this solution here. So to find the remaining factors and to factor this function completely, I can now use the fact that x squared minus 3x minus 4 times this x plus 2 are the products of x to the third power minus 2x minus x squared minus 10x minus 8. So I can find the remaining factors by factoring this quadratic that I got again from my quotient. So let's figure out what the factors of x squared minus 3x minus 4 are. So to factor this, we start by multiplying the first the coefficient of x squared with negative 4, which is going to be negative 4. And we want to find the factors of -4 that add up to this middle number of -3. So let's put -3 down there. So again, what we're looking for are two numbers that multiply to give me -4 and then add up. So multiply to -4, but then add up to -3. Well, the only way to multiply two numbers to get -4 is if one number is positive and the other one number is negative, because only a positive times a negative is equal to a negative. Okay? And well, the factors of 4, there's two possibilities. I can use 2 times 2, but that multiplies to -4, but that adds up to 0, not -3. So that can be the correct value. And I can use 4 times 1. 4 times 1 multiplies to -4, but this combination adds up to a +3, not a -3. So I'm just going to simply switch the sign. So I'm going to make the 1 positive and the 4 negative. And there, that works out. +1 times -4 is equal to -4, and +1 plus -4 is equal to -3. So that's the combination. So I can factor x squared minus 3x minus 4 to x plus 1 times x minus 4. Now, since we multiplied by 1, since the leading coefficient is 1, we divide these by 1, which doesn't change anything. So these are going to be the two remaining factors. So the remaining factors are x plus 1 and x minus 4. So we were given one of the factors, and we have two more. The remaining two are these. Let's see, let's do another example of this. So here we're given one of the factors. X plus 3 is one of the factors. And we want to, again, use that factor to find the remaining two factors, or the remaining factors to this function here. So let's use synthetic substitution to find the quotient and the factor of x plus 3 and this, for this. Again, notice that no power is missing. We start with x to the third. We have an x to the second power next to the first term and our constant term, so no reason to put 0 on any of them. So start by bringing down the 3. I'm sorry, that's -9. So this is now 7. -7, sorry. -7 times 3 is 21. 2, -6, and 0. Okay? So this quotient here, and by the division algorithm, we have 3x squared minus 7x plus 2. So this, multiplied with this, gives us that. So to find the remaining factors, I just simply have to find the factorizations of this. So let's figure out what the remaining factors are going to be, right? So we're going to start by multiplying 3 and 2. So 3 times +2, that's equal to +6. And we want the factors of a +6 to add up to that middle number, which is -7. Okay? So let's see here. So since we want a +6, we want the signs to be the same. So positive, but two positives gives us 6, but two positive does not add up to a negative. So we need both of these to be negative, actually. A negative times a negative times a negative is positive, and a negative plus a negative is going to be negative. Now it's figuring out what those numbers are. Well, we can try 2 and 3. 2 times 3 is equal to 6, but they add up to -5 and not -7, so that's not it. We can do 1 and 6. 1 times 6, -1 times -6 is equal to 6, and they also add up to -7. So those are the numbers we're going to use. We're going to use a negative 1, and a negative 6. So my factors are going to be x minus 1 and x minus 6. But since I'm multiplied again, my leading coefficient is 3, we're going to divide by that 3. The last time it didn't change because, well, we were dividing by 1. Let me go back to this one. We're dividing by 1. So dividing by 1 doesn't change anything. The numbers are going to stay the same. But here, since the leading coefficient is 3, dividing by 3 does give us a difference. 1 divided by 3 is 1/3. And 6 divided by 3 is 2. So these are the two remaining factors. Now, this factor can be written in a different way. You can write this factor as 3x minus 1. If you don't want to write a fraction there, you just simply move this to the front. Basically, multiply by 3 is essentially what I'm doing here, multiplying this entire function by 3, and you end up with 3x minus 1. But it's easier just to leave it again, just the way we have it, and just write it as this right here. Okay? You don't have to write it like this. It's acceptable, but since we're just simply looking again for the factors, we'll just leave it like this. So x minus 1/3 times x minus 2 are my factors. Okay, so now let's look at our last example. Now here in this example, notice that our degree of our function, our polynomial function, is degree 4. So I'm going to provide 2 factors so we can use synthetic substitution twice to bring this degree 4 all the way down to a degree 2, so then we can factor that quadratic. So let's start off with 5. Okay, so we have negative 5 times 5 times negative 10 is negative 50. Add that with the 58. That's positive 8, not negative. Positive 8. And multiply that with 5 is 40. And again, we end up with 0, like we should, because again, this is a factor. So all we're doing is verifying that x minus 5 is a factor. And now we have a quotient that is now to the 3rd power. So we're going to use now the second factor to get a quotient that will eventually be quadratic. So this one right here technically is 1x to the 3rd plus 1x to the 2nd minus 10x and then plus 8. But we can factor this again using their technique because this is to the 3rd power. So let's use the second factor so we can bring this down, divide it again, and end up with a quadratic. So bring down the 1, multiply, add, multiply, add, multiply, and add, and then again we get 0. And now this quotient is now a degree 2. So this is 1x to the 2nd minus 3x plus 2. So let's factor this. So again, my bad, times on the top and plus on the bottom. So I'm going to multiply 1 with positive 2, that's positive 2, and the middle term is negative 3. So what I'm looking for here again is the factors of a positive 2, two numbers that multiply to give me 2, but then add up to negative 3. Well, to get a positive, I need the signs to be the same. So either 2 positives or 2 negatives. Well, since they need to add up to give me a negative 3, they have to be 2 negatives. And well, this one's pretty simple. 2 is a prime number. The only factors of 2 are 1 and 2. And negative 1 times negative 2 is positive 2, and negative 1 plus negative 2 is negative 3. So my factors are x minus 1 and x minus 2. And since our leading coefficient is 1, we're going to divide by 1, and in that case, nothing happens. They're not going to change. Negative 1 divided by 1 is still negative 1, and negative 2 divided by 1 is still negative 2. So the remaining factors here are x minus 1 and x minus 2. So here, multiplying these four things together will end up giving us this polynomial function here. And there you have it. Cool. Very, very cool. All right. So this concludes, again, the examples on lesson 2.5. Again, the factor theorem and the remainder theorem. Now, again, if you have any questions, please send me a message on mine or through email. Again, I appreciate you watching, and I hope you have a wonderful day. Goodbye.